So in the previous class, we were discussing about. So we discussed about RLC or RCH. RL series, right? We didn't discuss about RLC. You saw RLC also. Okay. So RLC is also done. So I hope this year did this step, right? So last class I told you about a concept called as power factor. You remember what is power factor? It is defined as the ratio of the. Check your notes and tell me. It is defined as the ratio of. Those are online. Are you able to hear me?
Yes, sir. Yes, sir.
Okay. It is defined as the ratio of R divided by R and Z, where R is taken. R is the resistance, which is there, and Z is what? Impedance. Right. Now, so based on all these concepts, let's try to go to the next concept, that is average power in an AC circuit in a complete cycle. Average power in an AC circuit in a complete cycle. Okay. So we know that instantaneous EMF is. What is the instantaneous EMF? E is equal to E naught sine omega t. What about instantaneous current? I is given as I naught sine of omega t plus phi. Is it clear? So what will happen to the instantaneous power? So what will happen to the instantaneous power? So dark, no? So this will be equal to E into I. Because power is defined as the product of. How is electric power defined as? It is defined as the product of potential difference and the current. Right. So when this is the case, can I say T instantaneous is equal to E naught sine omega t multiplied with I naught sine of omega t plus phi? Can I say this? So this will be equal to E naught I naught into sine omega t into sine of omega t plus phi. Is that right? Now what we can do is, we'll multiply and divide it with 2, because wherever you have sin A into sin B, right? From your math, if you recollect, if you multiply this and divide it with 2, this can be written as cos of A minus B minus cos of A plus B. Remember this? Yeah? Because what is cos A minus B? Cos A cos B plus sin A sin B. Then what about cos A minus A plus B? Cos A cos B minus sin A sin B. So minus of minus should give you a plus, right? So that will give you 2 times, 1 minute, I'm sorry. That will give you 2 times sin A sin B, I'm sorry. Yeah, it will give you 2 times sin A sin B. So what I can do is, 2 times sin A sin B, I can write it as cos of, check it. Cos of, check it. What is cos of A minus B? Where am I able to hear the sound? The sound coming. So now are you convinced? So that is minus 2 sin of A plus B by 2 sin A minus B by 2. But I didn't write it as A plus B by 2. What you're saying is cos of single angle plus cos of another angle. But I wrote it as a compound angle form. Cos of A minus B is what? Cos A cos B plus sin A sin B. Cos A plus B is cos A cos B minus sin A sin B. So plus, so cos A cos B will get cancelled. That is why I wrote it like this. So cos of A plus B. So A minus B, sorry. Can I write it as omega t plus phi minus omega t? Observe. So when it comes to cos of A minus B, I can choose either of the angles to be A or B, because cos of minus theta is what? Why? Fourth quadrant. Right? So cos of omega t plus phi minus cos omega t into, sorry, into minus cos of omega t plus phi plus omega t. So then it will be something like this. It will be E naught I naught by 2 into cos of omega t plus phi minus cos omega t plus phi plus omega t. Is that clear? Is that point clear? Okay. So this whole thing has a bracket. Never forget that. Okay. Still, what am I holding to? E naught I naught divided by 2 into cos phi minus cos of 2 omega t plus phi. So what am I talking about? I'm talking about the instantaneous power is given by this value. So what is the heading? Yes, we need to find the average value. So when you need the average value, you need to go with the integration. Right. So whenever you have instantaneous value and you need the average over a complete cycle, you write it as integral of t instantaneous dt divided by integral of dt between 0 to t, and here also between 0 to t. Is that right? So if you recollect, this is what we did for average current of an AC as well. The first derivation. Correct? So if I take this as T average, then how do I write this as? Integral of 0 to capital T, E naught I naught divided by 2 into cos phi minus cos of 2 omega t plus phi, the whole divided by Integral of 0 to t dt is how much? Capital T. So I can write this as E naught I naught divided by 2t. I suggest everyone to write it along. Did you all copy it till this step? So here you have a dt as well. Is it right? So here you have a dt. Is there any doubt in this step? Is it clear? Okay. So E naught I naught divided by 2t into, what can I do here? Integral of 0 to capital T cos phi dt minus integral of 0 to capital T cos 2 omega t plus phi dt. Can I do this? So this will be equal to E naught I naught divided by 2t into this cos phi will come out of the integral. Cos phi into integral of dt between 0 to t minus. You remember integral of cos or sine over a complete cycle is always a 0. So this will be a 0. I repeat this, everyone concentrate. So here if you observe, I have cos phi dt. Okay. Here I have cos 2 omega t plus phi dt. Both are between the same interval 0 to capital T. That is in one complete cycle. So this is 0. This is capital T in one complete cycle. Okay, this is sine graph. But yeah, if I have to draw the graph for cos, it looks something like this. T by 4, T by 2, 3t by 2, and 2t. Sorry. Oh, sorry. So this will be pi by 2, pi, 3 pi by 2, and 2 pi. So 0 to 2 pi completes one full cycle. You have two small positive cycles which will add up to give you a half positive cycle and a negative cycle. Okay, have this in your mind. So here also I have cos phi dt between 0 to t. Here I have cos 2 omega t plus phi dt between the same 0 to t. But why did I put a 0 here and a 0 not here? Why did I say that this value is 0? So if you concentrate on one important term, you'll get the answer. Okay, so you're almost there. Omega? Omega is? You say. Try to complete it. You're almost there. Complete it. That's right, actually. So she's trying to say it is because of 2. See, omega t cancel out. Integral of 0 to capital T omega cos 2 omega t plus phi is what is 0. What is the difference? If you clearly see, stop forgetting, forget about physics, look at it in mathematical terms, you'll get the answer. It's very simple. If you see the difference, you'll get it. What is extra in the second term? 2 omega t. So it is actually a function of time. Means integral of sin x dx between 0 to 2 pi is 0. Whereas integral of sin phi dx between 0 to 2 pi is not equal to 0. What do I mean by this? So you need to observe with which function you're trying to integrate. If the inside function, the function which you're trying to integrate is a function of the independent variable, then the value will become 0. Else it is not a 0. Means sin phi would have come out of the integral And sin phi into integral of dx between 0 to 2 pi would have been 2 pi times sin phi. Are you able to understand the difference? So in a similar case, if you observe cos to omega t plus phi here is a 0 because it's a function of time. Okay. When that is the case, I can put a 0 here. Then what are we left out with? E naught I naught divided by 2t into cos phi. Integral of 0 to t dt is how much? Capital T. So capital T and this will get cancelled. This is how much? So this is the average value. Are you able to understand? So P average is equal to E naught into I naught divided by 2 times cos phi. Okay. Where this cos phi is what actually? This cos phi is what is called as power factor, because factor is a number that you multiply. Is that right? So factor, and what does mathematically factor mean? Suppose I have a number 36. 12 into 3. Can I write it like this? What are these 12 and 3 called as? And what is 36 called as? It's called multiple. So a multiple can be broken into factors. In a similar way, the average power consists of E naught, I naught, and cos phi. That cos phi is the one which decides the value of power. That is why we call it as power factor. Right? So this will be equal to, can I write this as E naught by root 2 into I naught divided by root 2 into cos phi? Can I do that? So what is E naught by root 2? It's called as ERMS, and I naught by root 2 is called as IRMS. So average power is given as ERMS into IRMS into cos phi. Is it clear?
Sir, how did root 2 came, sir?
Okay, root 2 into root 2 is 2. So E naught by root 2 into I naught by root 2 into cos phi. Is it clear? Now you see, if it is a purely resistive circuit, see, for a resistive circuit, what is the value of phi? For a purely resistive circuit, what is the value of phi? Phi is the angle between EMF and current. So when you talk about a purely resistive circuit, what is the angle between EMF and current? It is 0. So you'll put a 0 here. So when you put a 0, average value will be equal to ERMS into IRMS into cos 0 degrees. What will the answer be? ERMS into IRMS. To put it in simple terms, you remember ERMS is what actually? It is a DC value. IRMS is a DC value. So when you want to calculate the average power for a resistor, how will you multiply? You will multiply both the DC values. Okay. For a purely capacitive circuit, phi is equal to 90 degrees. What is the average value? ERMS into IRMS into cos 90 degree. This will be equal to 0. Okay. So average power is 0. Similarly, if it is a purely inductive circuit, phi will be again 90 degrees. And what will be the average power? 0. So what is happening in all the two cases? Whether it is a purely capacitive circuit or a purely inductive circuit, the average power is equal to 0. So now, if average power consumed by an AC circuit is 0, then the current is said to be wattless current. So if average power consumed by an AC circuit is 0, current is said to be wattless current. Clear? Clear with this? No, sir. So the next topic that we need to discuss is so write down the next heading as resonance condition for a series LCR circuit. Resonance condition for a series LCR circuit. So last class I explained you about resonance. You've heard this word, right? You would have heard about the word resonance in waves. So what does resonance mean? What frequency? We call it as forced frequency. So if the force frequency is equal to the, so don't write it down. If the force frequency is equal to the natural frequency, then the wave is said to have maximum amplitude. Okay. But the force frequency is equal to the natural frequency, then the wave is said to have maximum amplitude. Is it clear? So it starts vibrating with this value. This is for a wave. Okay, but here we are not discussing about a wave, rather we are discussing about a electrical circuit. Okay, so here what does the resonance condition of an LCR circuit mean? It is the same logic. What did I tell you at the end? I use the word maximum amplitude, right? Right. So if at all you have a series LCR circuit, right? And if you are able to define a condition where the current flowing through the LCR circuit is maximum. I repeat it. You have a series LCR circuit. Okay. And when you say that the current flowing through the series LCR circuit is maximum, okay, then that condition is said to be a resonance condition for a series LCR circuit. Okay. So write it down. So write down. Don't forget the word series. A series LCR circuit is said to be in the resonance condition. In the resonance condition, when the current through it has its maximum value. When the current through it has maximum value. Parallel நம்மளுக்கு இல்லடா, we need not worry about it. இப்போ ஒரு ஊருக்கு வேண்டியது யார் வருஷம் நீ வந்தியா மண்டே வந்தியா that is yesterday அதுக்குள்ள ஞாபகம் okay so series LCR circuit is said to be in resonance condition when the current to it has maximum value. Okay, now let's say this is the mathematical expression for current. The current amplitude, if I take it to be I naught, okay, the series LCR circuit, then what is the relation between I, E and Z? So I is equal to E divided by Z. Can I write it like this? So if I put I naught here, can I write it as E naught divided by Z? Right? So this will be equal to I. So this will imply that I naught is equal to, what is the value of E naught? It is the peak value of EMF divided by, in the place of Z, what can you write it? Z is equal to root of R square plus XL minus XC the whole square. Did you write this? So it is XL minus XC the whole square, right? So XL is equal to what? Omega L, and XC will be equal to 1 by omega C, right? So you can take these two values and substitute it. So when you do that, what are you going to get? I write it again, listen. For resonance condition, so for resonance condition, I naught will be equal to E naught divided by Z, which implies I naught is equal to E naught divided by Z is root of R square plus XL minus XC the whole square, right? So I naught will be equal to E naught divided by root of R square plus, can I write this as omega L minus 1 by omega C the whole square? Can I do this? Right? Now the next question is, for this I naught itself to be maximum, for this I naught itself to be maximum, Z should be minimum. Because this is equal to E naught divided by Z. So I naught to be maximum, Z has to be minimum, right? So when Z has to be minimum, observe, I have R square plus omega L minus 1 by omega C the whole square. This is what is you have as Z. Okay. If you observe this, this whole expression is sum of two squares. So when it is going to be sum of two squares, right? Is there a possibility for it to become 0? Sum of two squares, can it be equal to 0? It's never equal to 0. Is that right? Now the next question is, when it is not going to be 0, z cannot be least, right? Because it has to be the least value that the value under a square root can take is 0. But that 0 is in the denominator. You cannot put a 0. Can I do that? Because if z is 0, what would have happened? I naught would have been infinity, which is not possible. Infinite amount of current should flow through the LCR circuit. That's not the case. You want to make the current to be maximum. When that is a scenario, I can either make R equal to 0 or omega L minus 1 by omega C to be 0. Right? If I make either of the values to be equal to 0, then one of the values will reduce. The total value will reduce. Why is it so? Because I told you it is a sum of two squares which cannot be obviously equal to 0. Right? So either R could have been 0 or the expression omega L minus 1 by omega C could have been 0. But if R is 0, right, then there is no concept of impedance at all. So if R is 0, there is no concept of impedance. Because for you to define the impedance for a circuit, what do you need? You need one resistive element and either a capacitive or a reactor, capacitive or an inductive element. Is that clear? So what should happen? Omega L minus 1 by omega C is the only thing that can be a 0. When that is the scenario, I'll get omega square is equal to 1 by LC. Then omega will be equal to 1 divided by root of LC. And this 1 by root LC is what is called as resonance frequency. So omega R is equal to 1 by root LC is what is called as resonance frequency. Is it clear? So if omega R is 1 by root LC.
What is the subscript R denote?
R is resonance. You read it as resonance frequency.
Okay. Okay.
Okay. So omega R is 1 by root LC. Omega R can be written as 2 pi FR is equal to 1 divided by root LC, which implies FR is equal to 1 by 2 pi root of LC. So if you want the frequency in terms of radians per second, use this formula. That is omega R. If you want the frequency in terms of hertz, use 1 by 2 pi root LC. Okay. Is this point clear? No? The next thing is, we need to discuss about a concept called as sharpness of resonance, right? Okay. So for the first, we need to look at the graph. So look at the graph. If you draw a graph date, what do you want? Okay, correct. Omega in use. When will you use omega? Omega, WR, omega. Where will you use omega? When is omega? Where does that omega come from? There's a whole thing we are discussing the chapter. Omega and energy. What is omega? I've told this many times. It's called angular frequency. Okay. So if you want to see the variation of, observe this graph is the what is the heading? It's called sharpness of resonance, right? So if you observe this, if you draw a graph showing the variation between current amplitude with the frequency. Okay, when I say frequency here, I'm talking about the angular frequency. Okay, when you plot the graph, then there are three different graphs plotted on the same sheet, right? One is when the resistance is less. So, but before that, I want to tell you one important point. I told I naught is equal to E naught divided by Z, right? This is for a series LCR circuit. But in resonance condition, what is happening to Z? Z will be equal to root of R square plus XL minus XC, the whole square is there. No. What is happening to that XL minus XC? It becomes 0. When it becomes 0, Z is equal to R. So what is the meaning of this? During resonance condition, a series LCR circuit, please make a note of this point. During resonance condition, a series LCR circuit behaves as a purely resistive circuit. A series LCR circuit behaves as a purely resistive circuit. Is that point clear? So when that is a scenario, when you draw the graph showing the variation of I naught with angular frequency, then when the value of resistance is low, right? When the value of resistance is low, can I say I naught will be attaining a maximum value? So if I take three different scenarios, one is when the resistance is, let's say 2 ohm, 3 ohm, and 5 ohm. I've taken the least values. So out of 2, 3, 5, which one is least? Obviously 2. When the resistance is least, what will happen to the current? It will increase. That's what has happened in the first graph. Moderate resistance now 3. So when that is a scenario, you will have a graph like this. Okay. Similarly, when the value of resistance is least, you will have a graph in this way. Is that clear? In all the three scenarios, I naught itself is straight up. In all the three scenarios, I naught itself is attaining maximum value at which value of omega? So you are able to see it is attaining a peak value at a certain point, right? What is that point called as? Omega is equal to omega means if the value of omega is equal to the resonance frequency, the value of I naught itself will be maximum. That's what the condition told. I'll tell you what is the significance, don't worry about it. But when I spoke about resonance condition, what was the statement given there? The amplitude of current should be maximum, correct? So amplitude of which current? The maximum amplitude of the peak value. I naught itself should be maximum. So I naught is attaining maximum in all the three scenarios. Exactly at what frequency? At resonance frequency. So this graph is a very, very, very important one. Okay. So from this graph, we are going to define something called as sharpness of resonance. Okay. So what is the sharpness of resonances? Shall I proceed? First of all, did you all draw the graph? Draw this graph. Done. So for you to define the sharpness of resonance, you need a term called as quality factor. Okay. So you need a term called as quality factor, or in simple terms, you call it as Q factor. So what does this quality factor represent? This Q is defined as, it is defined like this. It is the ratio of resonance frequency. Okay. It is defined as the ratio of resonant frequency to the difference in angular frequencies, where the current value is I naught by root 2. I'll explain this first right now. So what is the definition I gave you? It is the definition for something called as Q factor or quality factor. What is it? It is a ratio of resonance frequency to the difference in angular frequencies, where the current value is I naught by root 2. Okay. Did you understand that? Did you write it down in the first place? I'll explain the meaning. So if I plot a graph, this is I naught, this is omega. So this is how the graph will look like, right? And what value is this? What value is this dot? Omega r. So on either side of omega r, I will take two values, omega 1 and omega 2, where the corresponding current value is I naught divided by root. Is it clear? Then Q factor will be equal to ratio of omega r, listen to this carefully, ratio of omega r to the difference in frequencies, that is omega 1 minus omega 2. Is it clear? So omega 1 minus omega 2, if I take this distance to be delta omega and this distance also to be delta omega, then omega r divided by 2 times delta omega is also called as quality factor. So I've taken the distance between omega r and omega 2 to be delta w, and the distance between omega 1 and omega r also to be delta w, because they are symmetric with respect to omega r. Okay. So if I add those two values, I get 2 times delta omega, and it is given as omega r divided by 2 times delta omega. Okay. So this value will be equal to omega r. Omega r is what actually? Name of omega r is resonant frequency. Any idea about what is this 2 times delta omega called as? So it is called as either transient bandwidth. So resonant frequency divided by, you call that as bandwidth, means width of the band of frequencies. Okay. So it is resonant frequency divided by bandwidth. Okay.
Sir,
Tell me.
how did omega 1 minus omega 2 become 2 delta omega? Can you tell?
Omega 1 minus omega 2 is difference. What is this length? This length is delta omega plus delta omega.
Oh, okay, sir.
Yes. Okay. So now, this is all about sharpness of resonant frequency. I hope this is clear. So where we discussed about Q factor. Okay, the question is, nowhere we spoke about the sharpness at all. Right. So what is the sharpness we are trying to speak? Is what we need to understand. Okay. Listen. So if there is an important question that we get arise first of all. Why are we studying all this? Logically saying, what will I do with RLC circuit, RC? So I don't mind. Right, but there should be a purpose why we are doing all these things. Right. So if you become an engineer, okay, there is a branch of engineering called as circuit theory. So as the name suggests, circuit theory, your job is only to design circuits. Since you will read it for 6 months, not your whole life. 3 months you will have some syllabus and 3 months some exam will go. So you'll have it in one of your semesters, you'll have something like this. Provided you take electronics and communication and electrical engineering. Otherwise, you need computer science, you need not worry about it. So what they do in the circuit theory mainly is, with the help of all the passive elements, they will design different kinds of circuits which are electrically functionable. In the sense, if you see all the topics that we have discussed, we discussed about resistor and capacitor connected in, resistor and inductor connected in, similarly RLC connected in series. But you can ask me a question. He asked me, so what about parallel? Parallel is not a part of our syllabus, but yes, you can connect them in parallel as well, depending on their functionalities. In the sense, where it works most is in the case of a tuning circuit, for example. So as the name suggests, sharpness of something, right? So you give to FM, right? So at places where there is no signal or there is some kind of weak signal, okay, you will still be able to hear, but with that hissing sound, you will have some sound disturbing event. But if you want to fine tune it, what will you do? As a human being, what first thing you will do as an end user? You will try to channelize something, right? Or you'll click on, if it is a digital system, you'll try to click on something called as tune and tell me the value. So for example, you have all these values, 98.3, whatever it is, 92.7, 98.3, what are all these things? Channel, okay. Why are they naming the channel with a number in a frequency? Frequency, okay. Frequency can be measured in terms of hertz, millihertz, microhertz, megahertz, gigahertz, terahertz, whatever it is. That 92.7, what are the units? It is megahertz. So when it is megahertz, right, it is actually falling between an electromagnetic, it is falling
Sir,
between, yeah, tell me.
sir, we can't hear you.
Now am I audible? Am I audible now? Others, are you able to hear me?
Yes, sir.
Yes, sir.
Okay, then you need to check your side once. Okay. See, for example, you have this 92.7, right? It is not degrees Celsius or Fahrenheit. It is megahertz, means you're actually tuning to that particular frequency, which this channel has reserved. Radio, whatever they want, they will keep it. That's a different, but that frequency is reserved for them. Okay. So this megahertz falls under the branch of an electromagnetic wave called as radio wave. So radio waves are the ones which you actually hear and use for communication. So why I'm discussing all these things is, sometimes when you hear the hissing sound, right, it is actually not tuned to 92.7. It is somewhere between 92.6 So what you're trying to do, that 0.6, you're trying to tune it to 0.7. For that, you need a circuit called as a tuner circuit. So because you're tuning something only, you're able to listen to that audio with sharpness. So you have a sharp sound coming out of it, right? For those things, we need to design a circuit at the back end. See, as an end user, you're only turning the knob, but who knows what is happening at the back end? The back end, you have all these circuits which are called as filters. Okay. So I don't remember exact filters, but I can tell. I don't know how the filters are designed. I read it, but forgot. Okay. So let's say you have a resistor and a capacitor which is connected in series. You choose certain values of resistor and capacitor in such a way that it will allow only certain frequencies to pass through. Okay, suppose I have a circuit like this, R and C. Suppose I want to use this as a filter circuit. What is a filter basically? Filter is something that filters only, obviously. It will allow only certain things to pass through. No? So you give certain input which contains a bunch of frequencies. And you want only certain frequencies to be passed. For example, in musical terms, we call it as low frequency and high frequency. Have you heard of it? Have you heard of this bass guitar and all those things? Very sharp instrument, which will be in lower volume. Bass instrument. So those who know music will understand what I'm trying to talk about. Okay. Sometimes in movies and all, when you have these woofers at your home theaters, now you'll be able to hear certain low frequencies, especially horror movies where they use it. Have you heard those things? So the one that they call it as low frequency. So if you want only those frequencies to be passed through it, you can call this as a low pass filter. Low pass filter, name is suggesting. Pass means what? It is allowing. It is allowing only low frequencies to pass. Similarly, you want to design a filter which is high pass. It will allow only high frequencies to pass through. So depending on whatever is your requirement, you will do it in that particular branch. So for all those things, the basics is what you're learning here. That is why we discussed about the sharpness of resonance, and the main application of sharpness of resonance is in tuner circuits. So if you want to have a tuner circuit where you want to obtain a sharp signal of something, it can be an audio or a video, then we design a circuit of this sort. Are you able to understand? But anyway, the application part is not a part of your syllabus. You're just introduced to the terms. Okay. So this is the outline. So that is why we were trying to talk about the resonance condition, because based on resonance only, I'll be able to define two factors. Quality factor, what is important? What is sitting on the numerator? Resonant frequency. Unless I know what is resonant frequency for a series LCR circuit, I cannot tell you what it is. What is quality factor? So for you to understand that, you had something called as resonance. But for you to understand resonance, you should have an RLC series circuit. But for you to understand RLC, you had series RL. Adikmala, series RC. Before that, so if you go in the back end, you will understand. If you go in the backward direction, you will understand by your study. So you need only a capacitive circuit. You need only a resistive circuit. You need only a inductive circuit. You need to understand what is RMS value. That is why the chapter started in this way. So having all these things in mind, right? So you'll be able to understand concepts of circuit theory. So if you see all the combinations, right? If you take it like permutation combination, we saw what is resistive circuit. We saw what is inductive circuit. We saw what is capacitive circuit. Then we saw resistor capacitor, resistor inductor. Then we saw RLC. But there is something that is missing. What is it? There is no inductor and capacitor connector, right? So that has no application under this. It has a completely different application. So if you see all the circuits that we discussed till now, you would have connected an AC source. So another topic here, we tell you a series RLC circuit connected across an AC source. Whereas for an LC circuit, there is no AC source at all. Capacitor is there, no? Second chapter, what does a capacitor do? What is the main application of a capacitor in the first place? You give charge, it will store. So the stored charge, what is it going to do? Is it going to store it for lifelong, or there should be some extraction out of it, right? What can you think of? You can think of a capacitor as a battery. Can you do that? So there is a question like this. Somebody asked me. So if you say capacitor can store charge, then why are we not using capacitor itself as a battery? Because capacitor is way cheaper. It will be this size only. You can easily charge it also. But why are we not using it as a battery? Why can't we replace a battery completely? To maintain the potential? More accurate answer.
Sir, capacitor gives charges only till the potential becomes equal.
That is okay. But in general, no, when you connect a battery, what will you do? You go and buy, you will try to connect it for at least months and years, depending on your usage. You want it for a longer duration. So battery is also getting discharged only. But a capacitor will also get discharged. It will be very quick. The moment you connect it, you lose the charge. Depending on what kind of a device you are using. Suppose 5 volt, I want another. I think I spoke about the LED light in the previous class. LED light today only I saw it requires 12 volt. Let's say I use a capacitor and give it 12 volt and try to connect it. It cannot supply the amount of current for a longer duration like how a normal PC battery does. Okay, because the rate at which it gets discharged will be faster. So think about it. Now, what did I tell you? In an LC circuit, what did I tell you? There is no battery used. So who is acting as a battery? A charged capacitor acts as a battery. So charged capacitor will discharge. So during the process of discharging, what will an inductor do? Previous chapter learned the recollect. When there is a change in flux taking place, what is induced? EMF is induced. So EMF is induced across the ends of a capacitor, ends of an inductor, and it will try to oppose the cause. So that EMF we call it as back EMF. In this chapter also I use the word back EMF. Somebody asked me a doubt also, right? So what will happen is capacitor, when it is getting discharged, inductor will start taking up all the energy and it will store it in the form of potential difference. What will happen? Capacitor will be completely discharged. Inductor will have the complete potential. Now, what can this do? Now this will start discharging and capacitor will get charged. So like the way the cycle keeps repeating, this is the outline. There is the outline. There is a conversion of energy taking place. About that, I need to explain you in depth of where it is applicable. Okay. So I hope these concepts are clear, right? The mathematical parts are clear. Today we discussed 3 important topics. What are they? Average power consumed in an AC circuit for a complete cycle. Then resonance in a series LCR circuit. Then we have sharpness of sharpness of resonance. So these 3 are the important concepts. So I suggest you all to make a note of all these formulas in one page. So yeah. So in the next class, we'll see about an LC. It's called as an LC oscillator. Yeah, oscillator, I'll tell you tomorrow. So it's called as an LC oscillator, and we have a concept called as transformer that we need to see. Apart from that, in the previous chapter, I didn't discuss about eddy currents. So that also I discussed. So in tomorrow's class, we'll be done with this. Then we'll do some problems based on it. And then we'll proceed to the next one. So yeah, any other doubt? Yeah. So those who are online, any doubt?
No, sir.
Okay, then we'll wind up.
Thanks.
Yeah. Akash, are you able to hear now? Akash, are you there?
Thank you, sir.
Yeah.